on image object detection with deep learning through neural networks, because this has been a very uh, developed area of computer vision over the last 2 years. So this paper came out in 2019. And here's just a simple image of the output for computer vision object detection. And it starts like a car. You can see the bounding box of where the car is located, the image label, and the accuracy for how accurate it thinks that it is that certain label. So we have the car with 99, a dog with 94, a horse with 99, and a person with 99. But also there's a horse in the background here and a person over here, and it did not detect those two. So it only detected what was in range. And how this works is that there's image classification and object localization, and its object detection is a combination of both of these. So you can see over here. So the image classification is that you could be given an image of a bird, and then it just says there's a bird in this picture. It doesn't know where it's at. The object localization just says it differentiates an object from the background within an image. So then object detection is differentiating the object from the background and then classifying it, giving it a label. So that essentially is what object detection is. And now, so here we can see this as an example through a grid with a picture of a dog, a bike, and a car in the background. The object, the bounding boxes here. So there's different boxes for everything, and it differentiates which ones are which. So here we can see, I guess, all the many boxes, and then the object labeling down here. So the dog in blue, the bike in yellow, and the car in red. It doesn't know exactly where they're at, but the bounding boxes does. So then it combines these two to give where the dog is at and that it is a dog, the bike, its location, and what it is, and etc. Now, adding the deep learning and convolutional neural networks to this is what makes it so it can identify each thing. So I guess I'm going to go back. This process here can be done multiple times, and that is a convolutional layer or a feature map. So this process is done many times, and with each feature map, there are different RGB values, pixel intensities, resolutions, etc. So that way it will increase accuracy with each layer and make predictions. And then these predictions are essentially fused together to form a image pyramid. And also these regions of interest, like they would, the regions of interest are like the dog, the object, like the objects essentially. So here we have the color map with different feature maps. So these are, I think, light differentiating and thermal type imaging to differentiate. So these would be one feature map, and this would be done probably 24 different times for most object detection. And here we can see back to the regions of interest. The algorithm will detect regions of interest, such as the person, the horse, the backgrounds occasionally. And so it gets those regions of interest and then runs the convolutional neural network on those regions of interest, determining if they are objects and what they are, giving them classifications. So the neural network aspect is this part right here, determining multiple, the image labeling on different parts of it. And many convolutions and regions of interest will increase accuracy. So as many feature maps as you can will increase accuracy, going back to that earlier picture where they were at 99% for accuracy for almost all of them. That is very good, but that would have taken a long time. So a lot of object detection applications nowadays use video. And videos, you can't have time. It needs to be quickly. You need to have so many frames per second, but also need to maintain high accuracy. So an accuracy threshold is used. So once an object passes, say 70% accuracy, it no longer needs to focus on detecting and labeling that object, just following it. And that is what a lot of the modern applications for object detection use, like YOLO, is called you only look once. So it looks once, it labels it, and once with high accuracy, once it passes a certain threshold, it will then just follow it. It doesn't have to relabel it every time. And YOLO itself runs at 30 frames per second with an average of about 60% mean precision accuracy. And this is with OpenCV libraries and CUDA, so it is GPU parallelized. And going back to that, the object detection applications, most of them nowadays are using videos, but this is going down to the different categorizations of object detection with generic object detection and salient object detection. Salient object detection is more just differentiating an object from the background, while generic object detection is just generic. It detects all objects in the background. And then this can also scale again down to multiscale adaptation with facial detection, or multi-feature boosting, or boosting forest with pedestrian detection. And I'm going to get into those. But in general, all the applications of object detection have been growing in the last 2 years because of processing powers increasing and speed increasing. So with the multi-scale representation, it means that in those convolutional layers, there are skip layers that provide consistency. So those provide blank information, semantic information, to help fill in the gaps with consistency. And so those convolutions will have more accuracy, essentially. And this can be used for facial recognition, limb tracking, and essentially is quality over quantity. So the image I have down here is it's a subcategory of facial recognition. It is facial recognition with lip tracking. So the paper here, they used lip tracking to track and monitor what movements different sounds make to try and read lips. And I think in the paper they got, of all words they said, they had about 40% accuracy. So lip reading now is a new thing. And then on the other side of the generic object detection is the multi-feature fusion or boosting forest. So this is merging, taking more convolutional maps and merging them together. So just more of everything, but this will obviously be slower. And this one I have as quantity over quality, right? As the image here, it just detects faces. It's not actually recognizing these faces, right? So it's just detecting them all. So there are plenty of detections all throughout this. And occasionally there are yellow or little blue ones too. These are, I think, low accuracy detections. But it mostly focuses on just detection in the background. While if I go back to that first image I showed earlier, it had the person and the horse in the background that it did not recognize, but it does recognize people and horses. So this would be something that aspect would handle. The other applications of object detection are a lot of medical imaging. The image on the left here is for detecting glaucoma in the eyes. And they trained it on just regular eye images with occasional glaucoma image to detect that. So running eye exams or medical scanning on people, they can use object detection AI to detect certain diseases or disabilities. And then the image on the right is also still like a medical aspect, but this is for fall detection, which is it maps the bodies of the limbs of each person and their locations. So this was using an Xbox Kinect, which is a pretty decent camera. So using light detection and depth perception, they were able to detect where the person is at in the room and if that person is standing up or on the ground. And so this has applications in nursing homes, in hospitals, etc. If someone has fallen down and nobody's there to witness it, kind of like a life alert. The other applications of this are deep sea exploration, security. There was a security application where gas stations had cameras with object detection, and it would detect and see if weapons are pulled, and then it would automatically trigger alarms if accuracy was over so much percentage. So Capatches recently, the image on the right here shows how Capatches can essentially be negated through object detection. Virtual reality, there's virtual reality examples where, along with the limb movement like this, you can incorporate gestures like hand movements, that kind of stuff into virtual reality. Shopping, I saw there was an Amazon warehouse or Amazon store that essentially would detect what objects are picked up and moved. A lot of the recent data and papers are about masks and COVID-19 and detecting facial recognition if everyone is wearing masks or not. And then other applications like attendance. There's many applications to object detection. So in conclusion, I have that within the last 2 years, object detection has blown up significantly, and there is not many recent papers on it, but it is still constantly growing. One of the examples I actually want to go back to is YOLO v3. This was not even in the paper. This was very new, and 30 frames per second with 60% average mean precision was about the best it was able to get at that speed. So as processing power will increase, the accuracy and frames per second will increase as well. So the speed versus accuracy trade-off slowly becomes less of an issue. There are many applications for this object detection, like we just saw, and the speed versus accuracy trade-off is slowly becoming less of an issue. And then here's all the references. There's many ways to learn OpenCV and create your own deep learning AI for object detection or facial recognition. Are there any questions?